Okay, so first of all, I'd just like to say thank you to the organizers of this conference. It's great to be able to get something out this year. So I'm Andrew Flynn, and I'm in the third year of my PhD at University College Cork. And this talk today is kind of elements of this paper that is currently under revision that I wrote with my supervisors, Vasilios Tachiridi and Andreas Aman. And the title of the talk is Multifunctionality and Behind the Scenes Bifurcations in a Reservoir Computer. And I suppose the first job I have to do is try to break up the buzzwords in the title. So the first word is multifunctionality. So multifunctionality is a fundamental feature of certain biological neural networks. And these multifunctional neural networks have evolved essentially to execute a multitude of mutually exclusive tasks without the need of rewiring. So this figure down in the bottom right-hand corner kind of paints the picture well for us today. A multifunctional neural network is essentially a single network that has been trained over time or evolved over time such that for a given input A, it performs task A. And then if I switch the input, the network stays the same, the connections are the same, but the same network essentially can also perform task B. So when you hear multifunctionality, what I want you to think is a single network that can perform many tasks, and how it does it is that its neuronal dynamics differ on the demand of a given duty. So multifunctional neural networks are well documented in nature. For instance, the medicinal leech, it's thought that originally this leech could only crawl, but then its environmental conditions changed and it didn't necessarily have an abundance of neurons. So as a useful resource of limited resources, it was able to, with the same network, learn how to swim. So a single network can switch between swimming and crawling. Likewise, with the European lobster, there's a single network that controls the switching between its gastric and pyloric mills. So essentially, it switches between its chewing and swallowing motion. And for instance, in us as well, in our pre-Boetsinger complex located in the brainstem, this guy is in charge of switching between eupneic, so that's regular breathing, sighing and gasping. So I suppose this network might already be quite well involved if you're switching between regular breathing to gasping if something has taken your fancy already so far in the conference. So the question I'd like to try to understand here is, can an artificial neural network be trained to exhibit multifunctionality? So if we take off our neuroscience shirts and put on our dynamical systems hats, what we have here is a neural network with more than one stable mode of operation. And from a dynamical systems perspective, what we could say is that we have a multifunctional neural network that resembles a multi-stable system. And if you could imagine, each task resembles a different attractor in the network state space. So if we compare and contrast these two figures here, what we have on the right is just some diagram illustrating what a multi-stable dynamical system is. I have the state of the system described by the vector x, which evolves continuously in time under some function f. And if I seed in an initial condition in the basin of attraction of attractor A, well, the system will evolve towards attractor A. If I change the input to be in the basin of attraction of attractor B, the system will evolve along towards attractor B. So you can see the stark similarities between what a multi-stable dynamical system is and a multifunctional neural network. So therefore, for an artificial neural network to exhibit multifunctionality, it must be trained essentially to facilitate a coexistence of attractors. So this is what we kind of want to achieve today. And the approach I took was to explore this problem using a reservoir computer. So reservoir computing is a reservoir computer is a type of neural network and a machine learning approach with particular success in vocal and image recognition problems, hidden variable observation problems, and most important for our problem, in reconstructing chaotic attractors. So the reservoir computer can be trained to mimic a trajectory on a chaotic attractor. So here we have the reservoir computer in action. This reservoir computer was essentially trained to imitate the dynamics on the famous Lorentz attractor. So we have the actual trajectory on the Lorentz attractor in the blue, and then the reservoir's prediction in the orange. So we see it's a nearly perfect match. It's able to follow the dynamics in a very similar manner. So with that in mind, the objective is to train a single reservoir computer to imitate the dynamics of different chaotic attractors based on a given input. So this is what we want to do today. So first, a quick outline of what reservoir computer in operation is all about. So the reservoir is essentially the hidden layer of the network. It's a network of, say, in neurons, and it's typically on the order of a couple of thousand. The state of the reservoir at a given time t is given by the vector r, and the internal connections of the reservoir is given by this im adjacency matrix. For my work, I investigated, so the reservoir can be, there's many different types of topologies you could use. I stuck with this sparse Erdos-Rini topology. And the key thing about this setup essentially is that the connections are initialized randomly and they're fixed. They're not trained. The internal connections remain fixed, but the matrix is rescaled to have a certain spectral radius, which invokes the notion of memory. And this parameter will be a key parameter in the results later on. So bear in mind this rho parameter. What you do essentially is you project some input signal into the reservoir through this input matrix to drive a response from the reservoir. And we compute solutions of this equation up here up until some time t listen to essentially drive the reservoir away from its initial condition. And it synchronizes in some higher dimensional state space in an equivalent matter to what the input is. And then we collect the data from some time t listen up until some time t train. So the aim essentially is to find an output matrix to replace the input and form a closed loop system. So we want to go from this drive response non-autonomous system to this completely autonomous system where we have the readout from the reservoir is able to, say, continue on what the input would ordinarily be. So we want to cross out our input and replace it with some readout layer. For our results, what we did is we used the ridge regression technique. So this is an offline batch method, if you will, whereby the W out matrix is just calculated using this expression, where the X and Y matrices are made up of, so we take a function of the reservoir state. Essentially, it's a trick people use to embed further nonlinearity into the network. So we just stack the state on top of the squares of the states. And this is our technique to get a W out matrix, essentially, to try to extract something meaningful from this 1,000-dimensional system. So back to what we want to do, we want to essentially train this reservoir computer to imitate the dynamics of different chaotic attractors based on a given input. So what is currently possible, say, is if I have two different chaotic attractors, say S1 and S2, I can have the same in matrix and W in, but different W outs are needed to construct the attractors. So I have a task specific matrix, essentially W out S1, and another task specific matrix W out S2. And if I seed in the initial condition, I will say, if I've done the training appropriately, I will reconstruct the correct attractor. What we would like, however, is to have the same im, W in, and W out used to reconstruct either attractors. So if I seed in an initial condition corresponding towards attractor S1, the same W out matrix can be used to reconstruct S1, and if I change the initial condition, the same W out matrix can get me S2. So to generate such a W out, we devised this blending technique. So what we do essentially is we concatenate and weight both training and target data matrices in the following manner. With this blending parameter alpha. So if alpha is equal to 1, the reservoir will only see data from attractor S1. And if alpha is equal to 0, then the reservoir will see data only according to attractor S2. And do the same for the input data. And we calculate the W out matrix as before. And the aim is to find an alpha such that we have the right blending of both attractors to give us this multifunctional reservoir computer. So what about our choices of chaotic attractors? I suppose the most basic case is to consider where the attractors S1 and S2 are already coexisting chaotic attractors from some known dynamical system. So we just need to get our bearings right here. So what we have is this test system is able to generate multiple coexisting chaotic and periodic attractors. And just for example, when I have the parameters chosen like so, and the initial conditions, two different initial conditions, I will evolve along either attractor A1 or attractor A2. So just taking this as an example, essentially, nothing too special about it. I want to train the reservoir computer to imitate trajectories on either attractor A1 or attractor A2, depending on the initial condition. So a single W out matrix can give me both attractors. To do so, we need to find some middle ground, right? So I mentioned rho earlier, the spectral radius of the adjacency matrix. Different attractors may require larger or smaller rho to be reconstructed. So different attractors might evolve along different timescales. So then the reservoir might need to have a stronger emphasis on one attractor over the other. We also need to find the right blending of the data. So if I'm weighing, if I put too much weight on one attractor, I might not be able to reconstruct the other. So if we consider our rho and alpha parameters here, and we characterize the predicted trajectory on attractor A1 and attractor A2 using this multifunctional matrix here. So essentially what we have here is we train the reservoir using a combination of rho and alpha parameters, and we get our multifunctional W out matrix. And if I seed in the initial condition to get attractor A1, and if I stay on attractor A1, so essentially if I look at the prediction after a long time, and if I'm still on the attractor, the point gets blue. Now, for instance, if I switch to the other chaotic attractor, the point becomes purple. And so I've put far too much weight on the other attractor, essentially, and the reservoir can't distinguish between the others. If the point is yellow, it means that the prediction has fallen towards some limit cycle. And if the prediction is green, well, the prediction has fallen towards some fixed point. So what we have here, essentially, from a grand scheme of things, is some non-trivial transitions between reconstruction and modes of failure. If we take the common blue area between these two figures, we're able to see the regions of multifunctionality. So if I pick any point in this plane here, so if I pick, say, alpha 0.5 and rho 0.7, I can say with confidence that I will be able to reconstruct either attractor using this multifunctional matrix depending on the initial condition. So here you have an example of the predictions here. You can't distinguish them too well because the prediction is so good, say. We're able to really map the climate very well. So we have the plotted here, the actual trajectory, the trajectory using the task-specific matrix in each case of attractor A1 and attractor A2, and then the multifunctional matrix which can do both. So can we be a little bit more creative with our choices here of our attractors S1 and S2? How about attractors from two different systems? How about we ask the reservoir or train the reservoir to reconstruct either the Lorentz attractor or this other attractor A2? So if we do the same tricks as before, what we find here is that we have our regions of multifunctionality, and we pick some point in this picture, we're able to reconstruct both attractors. So attractors from different systems can now coexist in the reservoir state space. So this is a completely new application area for reservoir computers. So it's quite interesting that the reservoir has this ability. So another question, so we're on to the next buzzword in the title, is these behind the scenes bifurcations. What else exists in the prediction state space? So if we pick a point where multifunctionality is achieved, say in case case 1, for alpha and rho equal to 0.5 and 0.7, how about we seed in many random initial conditions for this trained reservoir and observe the resultant trajectories? So here, if we apply equal weight, what we anticipate is that sometimes the random initial conditions will go towards attractor A1, other times it will go towards attractor A2, but more often than not, the prediction actually falls to some fixed point. So we have an additional fixed point in the plane that we didn't know about from before. So it exists behind the scenes, say. Likewise then, if I apply more weight towards attractor A2 here, and seed in many random initial conditions, I end up on the attractor A1, I end up on the attractor A2, I also end up on this fixed point in between both attractors, and I also fall towards a fixed point closer to attractor A2, which we call FP2. Then on the other side of things, if I apply more weight towards attractor A1, I end up in this picture where I have an additional fixed point closer towards attractor A1. So what we can observe from this is that we have additional attractors populating the prediction state space. These attractors were not involved in the training, and that's why we call these untrained attractors. What's more is that a small change in alpha can give rise towards a bistability of untrained attractors, which is where we bring in this buzzword behind the scenes bifurcations. So let's see what happens if we track the evolution of these untrained attractors with respect to alpha. We get these branches of fixed points. So we see that the fixed point in between both chaotic attractors actually exists for quite a large amount of alpha values, and likewise for the other fixed branches of fixed points. What we also see here is that we also get other regions of bistability closer to the extremes of alpha equaling 0 and 1. So what we observe is that when reconstruction fails here, so what I'm plotting here on the right-hand side is the predictions of the attractor A1 for a given alpha up here in the legend when I have the rho equal to 0.7. So essentially, when there is no data for attractor A1 seen by the reservoir, it quickly falls towards some fixed point. And as I slightly increase the data that the reservoir is seen, so increase the weight of the data that the reservoir is seen of this attractor, I will remain on the trajectory for a little bit longer, but I will fall towards some fixed point until I hit some critical point where I'm able to reconstruct the attractor. Also, you can see here some case where the prediction switches to the other chaotic attractor. But the important thing to take from this is that if you plot these points on this picture, these failures, when the prediction fails, they fall directly onto these branches. So what's also interesting is that, so we're quite limited in our technique here because it's kind of a brute force method. It's a 1,000-dimensional system. We're not really able to use the numerical solvers that are currently out there. So this is kind of a case of just a brute force method for finding these branches of fixed points. And as a consequence, we can't see the unstable branches. But ordinarily, these branches would be connected with unstable branches. And at these endpoints would be saddle nodes. What's more is that these branches look like connecting, so could we find some cusp bifurcations taking place? And when we look at increasing and decreasing rho, what we see here is that these branches do in fact connect. So we've found some behind the scenes cusp bifurcations. So what else can we uncover for other values of rho? Well, when we paint the full picture, it looks kind of like some interesting surrealist Picasso or whatever, but what you have here is this picture identifying what a failed prediction may tend towards. So plotted in the gray here is when we have a single fixed point existing behind the scenes, and in blue when we have a bistability. These kind of points of singularity here are the cusp bifurcations we just saw taking place. So there's quite a lot going on in this picture, and I could spend quite a lot of time going through all the bifurcations we find. But I suppose the most interesting thing I found was that we have a sequence of period doubling bifurcations, and we have a period doubling cascade, where essentially down in this little corner over here in the alpha rho plane, we're able to find a chaotic attractor. So what we have here is we're tracking the evolution of this fixed point FP6, and we see that it undergoes a Hopf bifurcation, and we look at the maximum and minimum of this stable limit cycle. And this limit cycle undergoes a sequence of period doubling bifurcations, and eventually there's an infinite sequence of them, and we have this chaotic attractor. So while we train the reservoir on data from attractor A1 and attractor A2, there is a completely different chaotic attractor which exists behind the scenes, which is quite interesting, right? So just to have a few words at the end, what we looked at in this talk was multifunctional neural networks, essentially. And I suppose the big thing to take from this is how much you can get from framing certain neurological features in terms of dynamical systems. So dynamical systems can act as a kind of a bridge here between what happens in the brain and what we can try to achieve in an artificial system. We also looked at different cases, exploring multifunctionality, and it also essentially opens up a new application area for reservoir computing. So essentially, if you had some application where instead of, say, changing parameters to change the attractors in the state space, you could upload these attractors into the state space of the reservoir and essentially design a controller to switch between the two different attractors from different systems. We looked at the non-trivial transition between achieving multifunctionality and different modes of failure. But we also exposed the existence of these untrained attractors and looked at the dynamics that these guys have on their own and these behind the scenes bifurcations. If you're looking for some further detail, of course, you can check out the paper. It's on archive or email me, but I'll leave it there. And I'd just like to say thank you for your attention.
Thank you very much. That was quite a nice talk. You have some questions in the Q&A. If you'd like to either read these out or I can, The first is how dependent are the parameter combinations, rho and alpha, on the specific tasks, attractors to be learned? Are there optimal combinations that allow multifunctionality for arbitrary inputs?
Okay, so essentially, these results are very much so dependent on the parameters. If you have two different attractors and they evolve along two different timescales, you'll need to have essentially some middle ground between the row, the memory, and the network, and of course the weight applied to the network. So the parameters are quite important here.
Okay, the second is, do you train the reservoir one after the other on the two systems, or do you perform training simultaneously? I imagine this affects the reservoir's multifunctionality.
Okay, so that's a great question. So essentially, we have the same W in matrix and the same in matrix, and we do the training, we gather the data for attractor one, say, and then we go back and we gather all the data for attractor two, and then we apply our blending technique, and then we have a single reservoir that, depending on the initial condition, can reconstruct one attractor or the other.
Okay, and then the last question so far is, how about more than two target attractors? What was the reservoir dimension in the examples?
Okay,
so I guess
another,
two questions.
Another great question. I haven't looked at more than two attractors. The way we have our blending technique set up is only for two attractors, but that's not to say here that you can have as many attractors as you like. So we know that there is research on, say, generating thousands of attractors in a given state space. There's no reason to say that the reservoir can essentially play host to many more attractors than the two we've tested it on. And yeah, so I was doing my simulations here. So the reservoir dimension, I had it set at 1,000. So 1,000 artificial neurons.
Okay, and then Richard asks, how does your method compare to the training of conceptors as suggested by Herbert Jaeger?
I'm not fully familiar with the training of conceptors by Jaeger. I'll have to read up on that. So I've got some homework. Thanks very much, Richard.
Okay, if there are no further questions, thank you very much for a nice talk. Very cool stuff. I think